Hello class. Okay, I'm just going to quickly go over and finish off question 2, part C and D, and then I'm going to move on to question 3. So questions C and D are actually quite trivial. So how far will block bounce back up the ramp if no energy is lost in the interaction? Well, we can just do a simple thought train by word. If no energy is lost, that means all the energy that was originally from the gravitational energy will go into kinetic energy, which will then go into elastic energy, which will then be released and go back into gravitational energy, which will put it exactly back up to the top of the ramp. And if 20% is lost, that means 80% is retained, which means it'll go up to 80% of its original height, which will correspond to 80% up S. So real quick, that will be for C. Okay, now we'll move on to question 3. Okay, so parts A and C I've already done. Sketch this potential and find points of equilibrium of this particle. Are they stable or unstable? So this is what the potential looks like when you sketch it, because you have an initial negative second derivative, which is dominated then by this positive a to the 4th term. The points of equilibrium are stable. They are here and here, because as you can see, the second derivative is positive at both of these points. Now we're going to go work out the points, all the points labeled for this graph, because that's what you're supposed to do when you sketch. So first of all, we can simplify this equation. V equals ax to the 4th minus bx squared is equal to x squared ax squared minus b. Now, we can find the roots of this equation by noting that there's obviously going to be a root at 0, because when x is equal to 0, this just becomes a 0 squared times whatever this is, so you end up with just v equals 0. So, roots at x equals 0, and obviously the other solution are going to be when ax squared minus b is equal to 0, ax squared minus b equal to 0, we have x squared is equal to b over a, x is equal to square root of b over a, plus minus, obviously, because we have two solutions on this graph. Now, we want to find the stationary points. We're going to differentiate this equation, so that's d on dx, ax to the 4th minus bx squared to 4ax cubed 2bx. We can simplify that. We get x 4a squared minus 2b, and we have a station sorry about that. It should be 2a x squared minus 2b. We have roots for this derivative at roots at x equals 0 and 4ax squared minus 2b equal to 0, which gives us x squared is equal to 2b over 4a equals b over 2a, so x equals square root of b over 2a plus minus. Now, that basically does C and D, A and C, explained for you. Now, this question B is a bit more theoretical, but we can see that's actually quite trivial. No particle in this field could escape to infinity because it would have to have infinite energy to do so. Because this potential on either side can reach any arbitrarily high number. So presume the particle had, say, 1,000,000 particles, you could a million joules of energy. It still wouldn't be able to escape this potential, escape the field, because the field could always produce a potential larger than the energy of the particle. So no, the particle could not escape to infinity in any way. It would always be brought back when all its initial energy is into potential energy, and it'll start rolling back down this potential slope. Now, what is the minimum energy the particle needs to get from side to side? Now, this is going to be given by the difference from the tro in the middle of the potential energy to the peak in the middle of the potential energy to the tro at the bottom, which is going to be this height here, minus b squared on 2a absolute value of that. Now, how did I get that minus b squared on 2a? Well, I just substituted in the x coordinate for the equilibrium point into the v equation. So let's do that. V is equal to a of, that's going to be square root of b on 2a 4 minus b square root b on 2a squared is equal to a b squared on 4a squared, so b on 2a should give, and now we can do some canceling out. You get b squared on 4a minus b squared on 2a, which gives us minus b squared on 2a. Now, obviously, remember, potential fields don't really, it doesn't matter the constant at the end of a potential field. A potential field is always about the difference between 2 points. So we can just take the absolute difference between the peak and the tro, and thankfully, in this case, the peak is at 0, so we just take the absolute value. We get E min is going to be this k value they gave times absolute value of the difference of the potentials, k times v peak minus v tro. Oh, yeah, I don't know how to spell tro. Sorry about that, guys. Tro is going to be k times 0 minus b squared on 2a, going to be k times b squared on 2a. And that is question 3 done. Move on to question 4 soon.